This is the Field's Homework Booklet, question 22. Explain why astronauts in an orbiting space vehicle experience the sensation of weightlessness. There are lots of words in this question, and if you read it carefully, it will help guide you as to how to structure a good answer. So you may consider how it is that we normally sense our weight. If you are standing on the Earth's surface, you are aware of your weight due to the normal reaction as the ground pushes back up on you. Now, for the astronaut in orbit, this normal reaction is lost. That's worth a mark. Next, you could explain why there is no normal reaction between the astronaut and the orbiting space vehicle. So this is all to do with the fact that both the astronaut and the space vehicle are in orbit. So as they are both in orbit around the Earth, they travel with the same orbital speed and the same centripetal acceleration. You could think of them as falling around the Earth together, and it is this that removes the normal reaction. Next, a calculation. A space vehicle has a mass of 16,800 kilograms and is in orbit 900 kilometres above the surface of the Earth. You are given the mass of the Earth and the radius of the Earth. You are asked to show that the orbital speed of the vehicle is approximately 7,400 metres per second. Now, if you were to look at your data sheet, you wouldn't find an equation for orbital speed. So it is up to you to think around any relevant equations that might bring in the variable of speed. When you do that, hopefully you will remember the equation for the centripetal force is equal to mv squared divided by r. And in this situation, the centripetal force is provided by the gravitational force. Equating these two expressions and rearranging allows you to come up with an equation for orbital speed. Now it's about careful substitution, and the key point to note is that the r in this equation is the radius of the orbit. Do be careful here, you must add the height above the Earth's surface to the radius of the Earth to give the radius of the orbit. So I've done this here, brought it down, and a careful calculation leads to the answer of 7,396. When you're asked to show an approximate value, it is generally a good idea to show one more significant figure. It proves that you have carried the calculation through yourself. In this case, one more significant figure would lead to rounding that matches the approximate value. So I've played it safe and given 4 significant figures. Next, a question considering energy changes for orbits. The space vehicle moves from the orbit that is 900 kilometres above the Earth's surface to a lower orbit of 400 kilometres above the Earth's surface. You are also told the orbital speed in this orbit is 7,700 metres per second. So thinking back to what you already know, you now have 2 different orbital heights and you have 2 values for speed, as you have calculated one previously as well. As before, be careful about the significance of the 400 kilometres. You need to add that to the radius of the Earth in order to find the radius of the orbit. You are asked to calculate the total change that occurs in the energy of the space vehicle. You are allowed to assume that the vehicle remains outside the atmosphere after the change of orbit. Use the value of 7,400 metres per second for the speed in the initial orbit. So you're looking for a total change occurring. Here you must consider both the change in gravitational potential energy and the change in kinetic energy. Now, it is possible to combine these two and use an expression for the total energy in orbit, which we have derived in class, and the equation is shown here. But please don't lift that from your notes, as it is not available on the data sheet, and so you would have to either remember or prove that equation first if you wish to use it. So I've gone for more first principles using the equations available. The change in gravitational potential energy would be the final potential energy take away the initial. The final gravitational potential energy is given by the equation minus gmm divided by r, where r is the radius of the final orbit. So you can see I've brought that down. We now subtract the initial potential energy, so there's my subtraction sign, and that is equal to minus gmm divided by its radius of orbit. You can see that this minus and this one would combine to give a plus, and you could then reverse these two terms if you wished. I've carried on leaving the negative sign outside the bracket and then carrying on with the substitution. So you can see minus g times the mass of the Earth times the mass of the space vehicle, and then we just need to multiply by this bracket here. That leads us to an answer of minus 6.78 times 10 to the 10 joules. Carrying on then, we need to consider the change in kinetic energy. So again, we can say it's the final kinetic energy take away the initial. So it is a half m v final squared take away a half m v initial squared. Please never ever subtract the two velocities and then square. That is mathematically different. So you can, however, take the half m out and then in the brackets have the difference between the two velocities squared. So final squared take away initial squared. That leads us to an answer of 3.81 times 10 to the 10 joules. The last step is to calculate the total change. And here you can see how important it is that you have tracked the signs carefully and that in both cases you have done final minus initial. You had a decrease in potential energy, but you have an increase in kinetic energy. So you add the negative change in potential energy to the positive change in kinetic, and that leads to an answer of 2.97 times 10 to the 10 joules.